Lab guy here. It has been a very productive day. I set out this morning to make it a goal to get the NBTV BIG Televisor working before the end of the day. And I was successful. You know, sometimes the old ways are the best ways, at least for somewhere to start. I went to the NBTV.org website and got the schematics of their reference design televisor, and I constructed their servo system, and I constructed their input video process and sync separator system. I did substitute the op amps in that latter circuit. No big deal. And everything works. And we will get into that here in a moment. But watch this. The NBTV BIG Televisor servo circuit is working awesome. This is one of the two built-in test patterns of the Aurora Designs World Converter. The other one is not very viewable, so we're not even going to look at that. But this is RGB color mode. The Aurora Converter can send black and white video to your RGB illuminator and also synthesize an orange image that is equivalent to the original mechanical television neon orange as it would have been viewed in the 1920s and 1930s. Let me demonstrate that. Here's black and white. The grayscale is excellent. The fine detail, I'm making finger quotes as I say that, is that X-shaped pattern that you can see in the center of the frame. Now note that that the frame that's centered on the screen is the main frame. There's a partial frame above and a partial frame below. But we're interested in the stuff in the vertical center of our screen right now. Now let's look at neon orange. This is equivalent to what a test pattern would have looked like on an original Baird televisor using a neon illuminator back in the day. Baird would have been very pleased to get grayscale like this in his earliest experiments. So let's go back to color. So that is the color bar test pattern across the bottom, and then a grayscale partial test pattern of dark to light on the top. Let's look at live video next. Here we have some miscellaneous corporate logos. This is one of my favorites because it looks so dang good. And now let's look at some live program. This is a DVD. Let's look at some DVD video and see if we can recognize some faces. Gary Owens, Goldie Hawn, Dave Madden, Ruth Buzzy, Artie Johnson, pretty amazing detail for 32 lines. What, me worry? Jack Lemmon, Gary Owens, Dan Rowan, Dick Martin, Barbara Feldon, geez, faster than I can say their names. Liberace, Joanne Worley. There you go, that's all the copyright material I can show you, I suppose. This ends our demonstration. Take it away, Dave Madden. Lab Guy's World, take one. Thanks, Jack Lemmon. So how did I achieve such remarkable results? Let's take a quick look at the setup. We have the Nipkow disc made from an old 33 1/3 RPM LP. It's driven by an industrial motor. My original motor drive amplifier is no longer involved. I'm using the NBTV circuit, and it is incredibly simple. It uses a total of 4 op amps if you do the monochrome illuminator, so I'm only using 3 op amps. The first dual op amp, an LM1458, is receiving the video into the termination from the world converter. The first stage is a simple buffer. It isolates the sync separator and the DC restoration from the outside world. The second op amp is configured as the DC restorer. We will look at that a little later in the video. In the second package over here, we have op amp number 3, and it is configured as the sync separator. It takes the sync off of the incoming video and turns it into positive 12 volt pulses, which then goes to the CD4046 chip, which is a phase locked loop chip, of which we are only using one of 2 possible phase detectors. We're using phase detector number 2, which compares rising edges. So the separated sync from the video, as it is, 31 horizontal sync pulses or line sync pulses with 1 missing pulse, is fed directly to the phase comparator. Coming back from the optical sensor on the Nipkow disc, we come into a receiving circuit comprised of a transistor configured as an inverter and level shifter. This wire has the pulses from the photodetector at 5 volts and they're active low. So when the light shines through a hole, this wire goes low. The transistor inverts that low going 5 volt pulse and pulls it up to a 12 volt pulse, which we feed into the feedback pin on the phase detector chip. The output of the phase detector is sent to a summing node through a 100K resistor, and at the summing node is a feedback from the motor voltage, and it's adjustable with this pot here. We'll look at that circuit later in better detail. and it sums those two voltages together and sends that product up to this IRF 540 power field effect transistor, which is in series with the motor. It's on the low side of the motor. The high side of the motor gets 12 volts through a 1 ohm resistor. It goes into the plus input of the motor, comes out of the minus input of the motor, minus input output, minus lead of the motor, down to the drain of this transistor, and then to ground through the source. The pin order on here is gate, drain, source. So this is configured as an analog power amplifier. The voltage generated at the summing node sets the voltage on the gate, which sets the current through the motor, and that's what controls the speed. The feedback loop on that is adjustable by this pot here, which I have been calling the free run speed for lack of a better term, as there's no circuit description on the NBTV website. They just say build this. And so I did, and after discovering that the mount that I built for this pot had one pin unsoldered, so I spent 3 hours troubleshooting trying to find out why this thing was acting wonky, and I discovered an unsoldered pin. Sometimes it would touch, and then the thing would work. Kind of. By this point I had substituted a lot of parts. So at any rate, that was the story of the development. In the end, this circuit works. So back to you, lab guy. Well, let's take a look at the circuits, shall we? Okay, I'm going to go through this quickly, so try to follow along. Starting in the upper left corner with J1, that is the video input, and R1 is our termination resistor. In my case, it's 75 ohms because my source is a true video output. In other situations, R1 would be a 10K ohm, such as the output of a sound card or tape recorder. It's AC coupled to the input of the first op amp, U1A. U1A, if you look at the lower right, you will see that the power pins on these op amps are tied to plus 12 volts and the negative pin is tied to ground. We're running the op amps single rail. Okay, single power rail. So the signals must exist between 0 volts and 12 volts. So I biased the input pin of U1A to halfway, to about 6 volts DC by way of resistors R13 and R14. This gives our incoming signal somewhere to develop after it crosses over the resistor. And it's floating, it's AC coupled. So as the video amplitude changes, it will move up and down DC-wise. The amplifier is configured as a ×1 buffer, has a high impedance input and a low impedance output. It immediately couples through C5, a 10 microfarad capacitor, to a DC restorer or a negative clipper. This op-amp configuration is set to take the AC coupled signal, which would normally be floating, and it will lock the tip of sync pulses, the negative tip of the sync pulses, to the voltage on pin 5 of the op-amp. The diode in the output feeds that DC level onto the signal line, on the video signal line, and charges the output side of C5 to the necessary voltage to clamp that signal to a known DC voltage. That voltage is determined by that resistor on pin 5. If you'll note that R5, RV1, and R3 are connected in series. Ignoring that RV1 is a pot, we have a voltage divider there, and it will be generating about 5 volts, 5 or 6 volts there, DC wise. So it will set the sync tips on the output of C5 to about 5 volts. It doesn't matter as long as they don't move. Then going back to RV1 and U2A, the third op amp, it's configured as a comparator. So U2A has a reference on the positive pin that is set on RV1, and you'll note that it is set just slightly more positive than the voltage on the DC restorer. So we are setting a slice level just up above the bottom of the sync pulse. When that is set correctly, U2A compares the video signal with that set voltage and extracts the sync pulse, inverts it, and outputs it as a 12-volt positive going pulse. The next circuit over, using U2B and the FET, is a monochrome LED driver. We will not be covering that here. So looking at the next circuit down, we start with the NIPCOW disc optical feedback circuit, which has a 5-volt regulator. I originally designed this to operate at 5 volts, which drives the high-intensity LED that shines through the holes in the edge of the disc onto phototransistor Q1. Q1 will output a low voltage when light shines on it and a high when the light is blocked. That is coupled over to Q2 through a 10K resistor, and when that pulse is high, it pulls the collector of Q2 low, and when the phototransistor outputs a low, Q2 will turn off, and the pull-up resistor R18, a 10K, will pull the line up to 12 volts. So it changes the pulse from 5 volts to 12 volts and inverts it and feeds it into the phase detector, which is U4, a CD4046. You'll note that that is called reference in. Then the signal input of the phase detector is our sync detected by U2A. Now when the motor is spinning, there's a train of pulses on pin 3, and when there's video input, there's a train of pulses on pin 14, the 2 inputs of the phase detector. Pin 13 to the right side of the phase detector is the compared output. It's a series of positive and negative going pulses that represent the differential of the 2 phase signals. When they're locked together, there'll be a small negative pulse and a small positive pulse, which cancel out when they pass through the 100K resistor R19 and are stored onto C11, a 0.1 microfarad or 100 nanofarad capacitor. The voltage on that capacitor is fed to the gate of Q4, the IRF540 FET, that is in series with our motor. That voltage controls how fast the motor will spin. There is also a feedback path going from the top drain pin of Q4 and feeds back the immediate voltage at the bottom of the motor through a voltage divider consisting of R22, RV4, and it looks like R21, 4.7K. It's filtered by a 10 microfarad capacitor and summed in with the phase voltage through another 100K resistor. This loop sets the free running voltage on the motor. The phase signal coming from the phase detector chip is added to that, and that is how the motor is controlled. If the pulses from the photodetector are faster then the reference pulses from the video. This voltage at the node of the two 100K resistors will go down. Well, the motor voltage will go down. And if the motor is running slow, then the voltage to the motor will go up. And that is how this circuit works in a nutshell. As if that wasn't enough for you, I have an insert video with some useful workbench advice. Watch this. When it comes to working with these white prototyping breadboards, which are really good, one of the difficulties you might encounter if you're on a really low budget, and many young people, especially high school students and even younger kids, and people without jobs and stuff who are trying to keep busy, they can't necessarily afford to go out and buy these little hookup wires that have the molded on pins. These suckers are very pricey. Now, over the past couple of years, I purchase a bag of these every time I go to Anchor Electronics, and I bite the bullet. I don't remember the exact cost, but they add up quick. They're expensive. So over time, I've accumulated quite a load of them. But the problem with them is they're either too short or they're too long for your circuit. And so your breadboard becomes a big, basically a Technicolor afro of loops of wire. And in some cases, if you're working in high impedance analog stuff, that can act as an antenna and pick up noise. And in low impedance, high current, it can either starve your circuit for current or radiate signals into your high impedance section. So a very low cost alternative is twisted telephone wire. Now, maybe you're a person in a low income area. Look for abandoned buildings and stuff, and especially businesses, or look where there's a dumpster. What do you call it? The open top dumpsters that are used in office renovation and demolition. A lot of times Cat 5 wire will get in there. You can get this out of Cat 5 and Cat 6 twisted pair like this. It's a single conductor, about 24 gauge wire, maybe 26 gauge wire, and it's usually in twisted pairs of various colors. Or if you're really lucky and you notice a telephone service technician and his truck, and he's got the manhole open, or he's at a pole, just walk up, be friendly, and ask if you can get some scrap snippets from him. They always have wads of this stuff in the back of their truck. I saw a fellow the other day. I was polite with him. We talked about the weather for a minute, and I mentioned that I use this stuff for breadboarding, and asked if he had any snippets. And lo and behold, he walked over to his truck and grabbed that little wad of wire. From the perspective of the phone company, this is something they would just throw in the trash. It's not even worth their time to put it in their recycle bin. What you see in their recycle bin is usually measured in tons, at least hundreds of pounds of this stuff. This is probably less than a pound of copper, and half the weight here is the plastic insulation. So if you go to a scrapyard to sell this stuff, if you don't have the entire back of your truck full to the top with this, you can barely get them to take it. They always take it, but you get pennies for the pound. So anyways, reuse is the finest form of recycling. So let's say you've accomplished all these goals. You got yourself a nice wad to work with. Working with breadboards, this small quantity will last for months. And of course, after you've cut various lengths, and stripped it and used it, you will have lots of pre-cut pieces in your inventory. So as time goes on, you have more and more of this available. But what I ran into with this stuff is it's twisted. And sitting here by hand and untwisting this, you know, it can be done. And it's not hard. If you got the time and the patience, that's the way to go. Now, you've seen me in previous videos twisting wire with my drill. So what I've done is I punched my drill into reverse. And I split the end a little bit like that, so I have something to hang on to. And hang on to it, and I go like this. And I now have two pieces of untwisted wire in a matter of seconds. And it comes in all kinds of candy colors to make your breadboards look good. And you know how to cut and strip a piece of wire. Get yourself if you're starting out and you want to play with some electronics, get yourself the white breadboard, and a small bench power supply. In fact, I'll tell you, you're looking for cheap power supplies, are you? You're looking for free power supplies? I cannot believe the number of videos where the experimenter is all, I don't have a power supply, I don't know where to get a power supply. Let me show you something. Just on my daily walks around the neighborhood and talking to people and looking in construction dumpsters, I find these things. I find these things all over the place. Little AC adapters. They are everywhere. People throw them away, they lose them, they drop them on the ground. And if push comes to shove, let's see if I have one. I do. You find USB cables laying around. Now, I need to dust more. And you find these laying around. You just snip the end off, plug that in, get your meter, plug that into your computer, and find your 5 volts output, 12 volts output, whatever these things run at. I think it's 12 volts. No, it's 5 volts. It's a 5 volt output. You got 5 volts to play with some chips and LEDs and things like that. You get 2 of these and you combine them. What I do is I plug them into a power strip that has a switch, and I wire up one of them as a positive ground and the other one as a negative ground, and you instantly have a plus and minus 5 volt power supply. How much easier and cheaper can it get? These things are amazing. This is 5 volts, 2 amps. That's a 10 watt power supply. Free. Completely free. So, yeah, you're talking to the cheapest guy on earth, by the way. This power supply was given to me recently, and I don't know the name of this connector. It's the latest in USB. So he even gave it to me with the adapter to adapt it to good old USB connectors. So at any rate, that's where you get your power supplies. And be nice to your telephone man and you'll get yourself some wire. Gravity is on again. I got to remember to turn that off when I'm making these videos. So you get your wire, and about the only money you have to spend is for the white breadboards. And if you can't afford the expensive wires, like those, which look, I think they look awful when you get done. You buy the breadboards, then you get some phone wire like this, just standard phone wire. Look for the old-fashioned, especially in really old buildings, the 50 pair cable. That's 100 parallel wires, and if you can get a piece longer than your arm, you're set for months. You can wire your breadboard completely full of wires. So that's Lab Guy's tip of the day. So there you have it. Some nifty workbench advice and a big televisor, a 12-inch Nipkow disc or Nipkow disc, or a throat warbler mangrove disc, however it's pronounced. And I guess I'm going to have to settle for that for today's accomplishments. It'll be tough. But I'll do my best to hide my disappointment. And I suppose until next time, I'll have to tell ya, Lab Guy out.